So, as we were saying, thank you for joining us. We are happy to have Patricia with us, who is a principal R&D engineer at CRIDA. And Patricia will share with us her experience in the traffic control domain for the attempt on measuring and assessing cognitive load for the activities that we see have been changing quite dramatically, quite a bit anyway in the last 20 years for a traffic controller, with the fact that the work is becoming even more intense, the traffic is ever increasing, and we need to also be able to verify how this is impacting the capacity of operators to deal with the workload that they are facing. The workshop is organized by the Irish Human Factors and Economic Society. We have myself and Diego representing the society here. Diego is the secretary. We wanted to say that the presentation is being recorded, and if you want to join the society or ask any information about this presentation or the others that we run in the seminar series, please refer to info@ihfes.org and the website for this. We ask you to keep your microphone and camera can be on or off, but the microphone off during the presentation of Patricia, and we'll have 10 minutes at the end of the presentation to have a question and answer session. So feel free to then open your microphone and ask the questions, or write the question in the chat, and we'll we'll basically repeat the question to Patricia for addressing. Patricia, thanks again for being with us. The floor is yours. I'll stop presenting so that you can take over.
Okay, great. Let me share my presentation. Okay. One moment. Can you see my presentation or not?
Yes, we can.
Yeah. Yep. Okay, first of all, thank you very much for inviting me to this session. It's always a pleasure to be with colleagues as you, and it's always a pleasure to talk about a topic that I really like, and is one of my areas I've been working on for many years. First of all, let me introduce a little bit of myself. My name is Patricia, and I've been working in the ATM domain. ATM, for those that who are not very maybe sometimes it's difficult to know the acronyms that we use in this specific domain. I'm talking about air traffic management. ATM is quite usual to use this ATM acronym. So I've been working in this ATM domain for more than 20 years. I'm an aeronautical engineer, and I have a Master of Engineering in air navigation. I've been working in research and development during all this time. So I'm an expert in validating the new concepts and the new solutions that are expected to be found in the future to improve the management of the air traffic. So in our work, and specifically in the activities that have been performed during these years, the analysis of the human factors have been essential to see the feasibility of the different solutions, or the different concepts, or the different tools, and the impact on the main role of the air traffic control, that are the air traffic controllers. So that's the reason why today I wanted to talk a little bit more about how we deal with human factors in CRIDA and also for ENAIRE. But let me explain a little bit in advance who we are, because I wasn't so sure the knowledge that you have on who is ENAIRE or who is CRIDA, on how the traffic management is about. So excuse me, my excuses if you already know all these things. But in any case, it's always good to remind why it's so important to talk and to study about human factors in air traffic management. So for your information, NAIRE is the Spanish Air Navigation Service provider. So it's a public entity, and NAIRE is managing 5 different control centers and also manages 21 towers. And who is CRIDA? CRIDA is it's research and innovation, research and development and innovation center. In fact, it was created in 2008 only to support the research and the development and the innovation of all the topics interested for NAIRE. And one of the topics of highest interest is this future concept to manage the traffic, and how these future concepts could affect on air traffic controller. Just to let you know, the air traffic controller, maybe when we talk about, we imagine or we think about an air traffic controller, we also imagine the air traffic controller in a tower, in a control tower, but the controllers are normally in control centers, where they have a radar screen, and they can see the flights on the screen. They are responsible for a volume of airspace, of a piece of airspace, and they are responsible to manage the aircraft within this particular volume of airspace. They are responsible for providing information to the flights that are crossing the airspace, but they have to plan the entry of all these traffics. They have to contact them. They have also to plan the conditions to for the traffic that are exiting that particular sector, that particular volume. They have to monitor the traffic in all time, trying to detect potential conflicts. That in fact, a conflict is a loss of separation minima. In Europe, the minimum separation minima is 5 nautical miles. So they have to check that the flights are at least 5 nautical miles separated in the horizontal layer, and 1,000 feet in a vertical layer. So if they detect some loss of potential loss of separation, they need to what we call they detect conflicts. They detect loss of separation minima. They have to plan a solution. They have to resolve the conflict, and it's quite is easy. I don't want to say easy, but the possible solutions they have is they are just 4 different solutions. That is to change the level of the flight, or maybe to change the speed of the flight. Imagine that we have 2 flights in trail, and you can in some way to change the speed of one of the flights to try to avoid this loss of separation. Vectoring, that is when the flight is taken to a different heading, and they have to go back to resume to the flight to the original path, or directly given these flights to direct to a different point, or to shortcut the flight path to try to avoid a conflict. They also have to coordinate with the collateral sectors, with other controllers that are there. And they have also to provide different instructions to comply with particular conditions for instance, at the exit points. So this is the main activities that they have to do. The activities are quite cognitive demanding, because at all time they have to process all the information that are around in terms of traffic, and they have to search for different solutions in the situation. There is some kind of loss of separation. And there is one thing that I would like also to explain, that is what is the demand and capacity balancing. So imagine that the traffic is or the air traffic controller is controlling this volume of airspace, what we call a sector, but there are more flights coming into the sectors without any restriction. So the thing is that the controller can suffer a mental overload, and this is something that the system try to avoid at all time. If there is a mental overload, it's because there has been a bad planification, because there dedicated area within the NSPs, and also from Eurocontrol, that is the central organization that is taking and responsible also for the safety in Europe. The different NSPs, the different navigation service providers, need to check and need to see the flights that are going to enter to every particular sectors some hours in advance. This is very, very important, because otherwise, if there is no any kind of checking of the flights that are crossing to that particular sector, we can have a safety issues for the controller, because the controller cannot manage the situation, and we can have an incident. So that's the reason why some hours before the operation, if the number of traffics are exceeding declared capacity of that sector, the air navigation service provided has to manage, or have to decide to make some solutions, some measures, what we call demand and capacity measures. One of these measures can be to say to the flights to change the flight level. Just changing the flight level, they could avoid crossing that particular sector, or to reroute the flight plan, to reroute the path of the flight, trying to avoid to cross that particular sector. Other measure that maybe we are more used to here is the imposition, the delays. When imagine or remember, because I'm sure that you have already heard these reasons from pilots when we are our flights are delayed. Is because of this reason, we need to keep on ground. We need to delay the time the flight can take off, just to avoid a situation, a hotspot in the airspace that can create a lot of flights in the same place and at the same time. So some of the flights have to be delayed on ground. And their solution could be to split the sector. Maybe if there are enough resources, the sector can be split in 2 or in 3 even. And you can put more controllers to manage more flights. This is something that can be done. So one of the things that we do in CRIDA for an idea, and have some kind of methodologies quite similar to the ones that we are going to explain today, is to measure and to predict the mental workload of the controller. For us, is one of the most important things. That is the measurement of the mental workload. This mental workload, we can use it not only for prediction, that is the situation. If we can predict the mental workload of the controller, we can use that information to design the demand and capacity balancing measure, the one that I've told you in advance, or we can assess this mental workload to check, for example, about human factor aspects, to see or to analyze incidents or safety incidents that could have occurred. So we can use in different ways these measurements of the mental workload to mitigate the mental workload, and also to design solutions to mitigate this mental workload, and also to analyze in a post-processing phase, in a post-processing, to post-process all this mental workload, and to validate or to check some human factor aspects, or to check if the demand and capacity balancing measure worked properly. So this is the 3 points that I would like to talk to you. It's about the COMETA tool. That is the tool that we have to measure workload. We have 2 versions of COMETA. One that is based what we call about events, and the other one that is based on cognitive complexity. So what is COMETA? COMETA is a prototype. I'm going to take out candy because I'm feeling a little bit cough. Sorry.
Take your time, Patricia, don't worry.
Okay, COMETA is a prototype that has been developed by CRIDA for an idea to estimate the workload in terms of cognitive demand and cognitive complexity for the en route phase. This is based on a controller psychological model that takes into consideration of the cognitive processes and also the attentional resources that are needed for these cognitive processes. As I told you before, we have two versions. That is the COMETA based on controller events. Another one that is based on the cognitive complexity. Sorry. I hope it's not so disappointing. Okay. Imagine that we have this air traffic controller. The traffic controller is in an operational environment. The traffic controller has to manage a situation of traffic. So this psychological model has different components. One that describes all the cognitive processes that are involved when the controller is managing the air traffic in that particular operational environment. And the other model, or the other component, is related to the mental resources that are needed to process all this information. So in the reality, you know that we have our brain, and this brain, in different parts of the brain, we have the different cognitive processes can even be located directly. Imagine that a flight is calling. The controller needs to perceive this flight. The two main channels the controller uses to detect the flight is through the visual and auditory the channels, and then the controller comprehends exactly the flight that is coming. The controller projects where the flight is going to be. The controller tries to see or to plan if the flight is going to have some kind of loss of separation, and monitor or evaluate if some kind of instructions are needed to be taken to avoid this loss of separation. And all of this taken into consideration
the knowledge that the controller has to do all this work. So at the end, the cognitive structure for an ATCo, the model that we have adopted to emulate this cognitive process or this cognitive structure is the model coming from Houston and Hasman, where all these different cognitive processes can be allocated and in the different places. And the model or the component related to the mental resources, we have adopted the model coming from Gopher. This is the energy that is needed to be taken into consideration in these cognitive processes. In one hand, we have the demanded resources that are really dependent on the complexity of the task, and in the other side, we have the available resources. They are more related to the level of activation, the individuals factors, or even the temporal factors. So the relationship between these two different resources, the demanded and the available resources, is what is called the mental workload for the controller. So once I've told you about the cognitive or the psychological model that we have taken as a basis, we have been thinking, or we have developed two different ways to computerize the model, because at the end, it's okay. We need to investigate about the different models, the different theories, psychological theories that are important to better understand the behavior of the controller, but we also need some kind of quantification of this mental workload to make decisions, as I told you before, maybe to make or to decide about the demand and capacity balancing measures, or to analyze different human factor aspects. So the COMETA, this tool, we have to, as I told you, we have these two versions. The first one, COMETA events. For that, we need some events that have occurred during the real or simulated situation. We do not need to have only real situations, but can also gather these ATC events even in a simulated scenario. We need a task model. This is something quite important. We need also a mental resources model related to the tasks, and we also need a calculator of the mental resources. As for the complexity, the most important things that we need are what they call the mental abstractions that the air traffic controller make to manage the traffic, that are the flows, that are the traffic patterns, critical points, that are the points where conflicts are expected to occur, or some common characteristics of the traffic. And maybe you can ask why we are using one model, one tool, or one version, or a different version, but let me give you some more details on that. If we go to the COMETA based on events, so what we do, the tool, the model that is behind, or the computerization that is behind the tool, is that first we have this traffic situation, and we gather all the ATCo events. These air traffic controller events. These air traffic controller events, as I told you before, can be taken directly from real traffic or real situations, or can be taken from simulation, or even fast time simulation. This is something that can be done, and we can extract from that situation about the main activities that the controller is doing, when the traffic controller is contacting the traffic, when it's releasing the traffic, when it's changing the flight level because of a conflict, when it's vectoring, so different events. So what we have is a task model. That is a generic task model. that we have been working for a long time with different expertise, operational expertise, and also colleagues from other domains like psychology. So what we have done is for every one of these events, we have defined different tasks that are supposed to be done in generic by the controller. So if the controller is going to release a traffic, there are two things that the controller has to do. The first thing is to check the conditions at the exit. When we talk about conditions, we talk about the flight level. The controller has to release this flight to the next sector, or maybe also the point where the controller has to release the flight, or even the speed. So we are talking about these conditions. So the controller has to check if these conditions are already, the flight is compliant with this conditions. Otherwise, the controller has to provide instructions to the flight to ensure that these conditions are complied. So for every one of these events, we have a set of tasks that are defined in time, the duration of the task, and also not only the duration of this task, we also have identified the cognitive processes that are involved when performing every one of these tasks. Here we have the model of the cognitive structure, because here we have, for every one of the tasks, if we are talking, if the perception, comprehension, projection, decision making, or execution are in place. And also in a generic way, because this task model is for a generic controller, this is the common activities or the common tasks that the controller perform. We have also identified the resources that should be that are typically associated to every one of these tasks. Okay, so imagine that the controller is not only releasing the traffic, the controller is doing at the same time assuming traffic. At the same time, the controller is checking, giving instructions about the level changes, vectoring, or giving information. So at the end, what we have is a lot of tasks at the same time in parallel. And what we have decided to use to measure quantitatively the workload, in this case, is with the multiple resource theory. That is a classical theory that coming from Wickens. That at the end, what Wickens was saying is that our brain is divided into different pools, and these pools of resources, and when the task is competing for pools that have some kind of interference or for the same pool of resources, if there are different tasks that are competing for the same pool of resources, there's going to be some kind of interference. Imagine that the controller has to talk and to listen at the same time. According to Wickens, there is some kind of incompatibility between these verbal and auditory cognitive processes. So what we have taken is to take these interferences, and what we have done is to translate all these weights to this formula, and at the end we have for environment the quantification along the time of the workload of the controller. And this is a little bit old because we have improved a little bit, but for this presentation, it's quite self-explanatory. This picture is the tool that we use for that. Here we have the distribution of this cognitive demand that has been taken from from the formula that I have just shown you to you before. This is also the distribution of the different cognitive processes. This is the information of the ATCo events or the ATCo tasks that are in the scenario. And this is a map of the flights that are crossing the scenario. So with this information is quite useful because we can identify which cognitive process is more demanding, where and why are the reasons there is more mental workload. And we can identify with this kind of information maybe new designs of new tools or new procedures that are going to help controllers to make their work. So this tool, when these events are known, for us is quite useful, as I told you before, to assess not only the human factor aspects, but also it's possible to assess the capacity of the sector. In fact, with this kind of cognitive model, ENAIRE estimates the capacity of the sector. It's checking if the controller has obtained, of if to avoid the controller reaching the overload. They identify a maximum number of aircrafts that can enter that sector using this kind of models. So it's a nice model to estimate the capacity of a sector. The issue of this model is that it takes a lot of time to model the tasks, and also to model the resources associated to the task. This is something that is already done, and ENAIRE have been working in this method and this model for more than 20 years. So you can imagine that this model has been refined, modified, and tuned to obtain a calibrated model. But it's true that it's hard to elaborate a model of the task, and also the cognitive resources model associated to these tasks. Sorry? I don't know. Okay. And the other negative or disadvantage that I could say about that is it doesn't provide useful information, for instance, for demand and capacity balancing. And this is something that we tried to use in some validations in the past. And if you say to a person who has to decide which is the flight who is creating more workload to the controller, which is the flow that is creating more workload to the controller, which is the measure that I should apply some hours in advance to reduce the workload for the controller, is not quite useful, because it only provides a global figure of the mental workload and the different cognitive processes that are involved in the activity. So that's the reason why we started to analyze the cognitive complexity. The cognitive complexity is also part of the psychological model that I talked to you at the very beginning. According to this, the same authors, where we have taken the psychological cognitive model, they define this cognitive complexity as the cognitive difficulty of controlling air traffic situation. The controllers tend to search for patterns, traffic patterns, to shape and to manage the objective complexity of the situation. It's what they call the structure-based abstractions. So that they are mechanisms to simplify the complexity of the situation. So in this picture, you can see a sector with some flights. maybe for a person who is not a controller, we can see there just a set of flights within a sector, but a controller quickly, the controller will identify that these traffics are going through the same flow. There is one traffic that maybe is not is a slow flight, and that's the reason. Maybe this slow flight is impacting negatively the sequence, a smooth sequence of flights, or maybe the controller is detecting that there is some flights that are out of the normal or the standard paths. So the thing is that the controller tries to make this mental abstraction to manage in a better way the complexity of the traffic. So which are the main abstractions that the controller usually do? I more or less, I told you before, this is the standard flight that is the patterns, the common patterns, that the common flight paths of that can be clustered in a common flow. And they do that because these simplify the calculation of the dynamics of the flight. They also have try to tend to group the flights with common performances. For instance, the flights with a similar speed, they are managed in a common way. The calculations are done in a common way, and the flights that are maybe slower than these ones are put in a separate path, trying to because they're not belonging to the same group. And also they talk about the critical points, that are the points where they expect to find common, they normally expect to find conflicts, because at the end, the critical point, they are usually the points where different flows or these standard flows are crossing, and they expect of flows that have to be merged. So they expect to find potential losses of separation. So the thing is that when we were thinking about these mental abstractions, we said, okay, so all of the things that do not facilitate build mental abstractions, all those things that do not facilitate are out of this they are out of these abstractions. These are going to be to create complexity, cognitive complexity for the controller. So with this hypothesis, or with this assumption, with this assumption in mind, so if I repeat again, if all these things, these mental abstractions are mechanisms for the controller to reduce cognitive complexity, we are going to think about all the things that do not facilitate these abstractions. And with these things, we have built a tool to measure the cognitive complexity. We have been working also with the NIDE staff, with the operational people, to identify that these are the most important factors that create complexity and create a cognitive complexity to the controller. The first thing is that those flights that are out of standard flows are creating complexity. When these standard flows are interacting, they create complexity. Aircraft with non-common performance within a flow, the example that I've given to you before, the slow ones is a factor for complexity. Or for instance, if we are talking about an en route sector where the flights are usually crossing the sector at the same level, if there is a flight that is not crossing at the same level, but is evolving because it's climbing or is descending, this flight is creating also complexity, or for instance, if there are conflicts that are not are located in different zones, are not belonging to these critical points. Remember that these critical points are the areas where the controller are expecting to find a conflict. So if there is a conflict out of this critical point area, it's going to create more complexity. So with those factors, at the end, we have built a tool that runs in real time, taking the flights directly from the network manager, that is from Eurocontrol. And we have this information quite in advance. We can do it with 1 hour, 2 hours, 3 hours in advance, not much more, because if you go very farther in time, if you want to predict longer in advance, the uncertainty of the flight paths is going to be worse. So this tool is usually used 1 to 2 hours in advance. So we can see 2 hours in advance if these flights are belonging to standard flows. The flows are already known in these sectors. We can know in advance if these flights are in evolution or they are not in evolution in the case of a en route sector. We can see in advance if this flight, if the flows are crossing, because they are going to we are going to have flights crossing the flows. Sorry. And then we are going to have information about the complexity of every one of the flights, the complexity of every one of the flows, and the human operator can decide the different measures that can be applied to avoid a sector is overloaded in the future. If you detect that the sector is overloaded, the operator is going to decide this flight has to be removed. And when I say removed, is removed from this sector in that particular time. So I'm going to apply a level capping or a rerouting or a ground delay. This is something that the air navigation service provider has to decide several hours in advance. So this tool is basically used for prediction. It provides information on these hotspots and the flights and flows that are more complex, and then to implement measures. And we have to say that it's under validation by an aire operational staff, because the intention is to include this information in a tool to be deployed within the control centers. And I think that this is the end of the presentation. Sorry if it's been I've extended. I've taken more time than I initially planned, and sorry for my cough.
So no, thank you, Patricia. That was very informative, and I was hoping that some of the people in the audience might actually have questions for you, because what I think is useful in the presentation is also how you basically, the data collection that you can do as part of CRIDA was structured as like a design of experiment, effectively, because you identify what were the cognitive functions that could be observed and what data could be considered as part of the contributing factors to an estimation of the workload according to the multiple resource theory. Can I ask you, in over the years, what were the most, let's say, in a way, the best estimation that you reached of this elusive concept of mental workload, in your opinion, the ones that you think are very easy to apply or easy to be deployed, even in other contexts?
You mean between these two methods, which is the For me, the both of them are really good, but the application is quite different. The first one, more related to this task model, is useful if you know in advance the controller events, and if you have in advance a task model. In prediction, it's quite difficult. Okay, you can use the different techniques, but in prediction, some hours in advance or days in advance, you don't really even know the tactical activities, the activities that the controller is going to do. So that's the reason why this method is quite good when you are post-processing a situation, in a situation that has already occurred. You have these events and then you can directly measure the workload. So for post-processing, this method is quite useful. And but that's the reason and I see so useful in post-processing when we try to use it for prediction. We didn't have all these controller events. In prediction, you more or less know in advance when a traffic is entering a sector, when it's leaving a sector, but you don't exactly know if there is a potential loss of separation, the resolution of the conflict, because the resolution of the conflict is quite dependent on also on the controller. And also in prediction, because of the uncertainty of the flight path, is quite naive to identified conflicts, because if the flight is entering some minutes later, maybe the conflict is not going to happen. So that's the reason why we decided to move to this cognitive complexity, because the cognitive complexity at the end, we try to use flows, we try to use flight plans, and we do not know to the minimum detail of the conflict. This is something that we do not use. We do not calculate because of this uncertainty. So I cannot say that if one method is better than other method. Is that I say that we use both, but in a different context.
Thank you, Patricia. There is a question in the chat. Alison, you feel free to ask the question directly. But anyway, the question says that she enjoyed the presentation. And can you tell us a bit more about what indicators you use to determine how a controller has perceived, comprehend the situation correctly, and what factors can be observed? So, question also about situational awareness, if there is a way you detect.
This is quite difficult. And this is something that we have, that's the reason why we have needed the support from psychologists to tell us exactly when the controller has to do a particular task, the cognitive demand in these different cognitive processes. Because unless maybe you use some kind of physiological measures to monitor the cognitive demand, sometimes it's quite difficult to identify if this is this cognitive demand is can be allocated on perception, or can be allocated on comprehension, or can be allocated in a different place. So maybe this is one of the I told you in advance, the disadvantages of the method, because you at the end you have to make a lot of assumptions, and that's the reason why we are engineers, but we also work with also the experts on these kind of things, on these cognitive theories, and we have been working with them to identify in the tasks that the controller has to do. which are the different cognitive processes that are involved in the task. And if we need to compare two different tasks, which one has more cognitive demand in a perception in comparison to this other, or maybe which one has more cognitive demand in decision making in comparison to this other. So at the end, it has been a continuous work along the years to tune and to define this model, this task model and the resource model.
Thank you.
You're welcome.
I think Carlos had
We
a
have-
question here in the chat. If you want to
Before
say.
Alison, we had another question from Lawrence as well.
Ah, sorry, I missed that. Yeah. Lawrence, do you feel like asking the question directly? Or we repeat it for you? Okay. The question in the chat is, have you explored any other more direct measure as opposed to predictive or self-reported personal workload factors of the operators, such as experience, fatigue, etc.? And if so, what method would you use for?
Yes. For sure, we use subjective measures, and also we use physiological measures. The subjective measures, the online measure is only used in a control environment. I mean, in a laboratory or a validation of a concept, because at the end it's a very intrusive measure, and you cannot ask controller every 2 minutes or 5 minutes the load or the workload that they are feeling. And also in these validation activities or simulation activities, we also use the typical NASA TLX questionnaires or similar questionnaires to ask for workload. And the other methods that we have tested are the eye tracking. We have been using also eye tracking in validation. And also recently we have used also eye tracking to support some validation of a remote control tower, where they wanted to detect if they saw the flights in a proper way. But okay, yes, we use also eye tracking to check or to validate the mental workload. The issue with the eye tracking is that as there are a lot of different light in the room, or even the different screens that they use, we discarded to use the pupil size, the pupil diameter, the difference of the pupil diameter, because of the effects of the light. But we have had positive results with the blinks, or with the saccades movements, or things like this. Yes, this is something that we have used. And also in collaboration with other universities, we have been starting to check also EEG, and also the heart rate variability. But honestly, by the moment, the eye tracking is the best and less intrusive way, but always in a validation environment, in a control environment.
Thank you. I think that addressed some of the questions that Carlos also wanted to ask. One very last question, anyone? Go for it, Alison. Ask it.
Hello, apologies for the multiple questions, but I can't help myself. It's such a fascinating area. I'm involved in looking at decision-making and situational awareness on the flight deck, and we're constantly looking towards the single pilot operations, how that will change the tasks on the flight deck. And much research has gone into that aspect of things. Can you tell us what you think the impact will be on the individual controller, and how much research has been considered from an air traffic control perspective about the impact that single pilot operations might have?
Okay. The single pilot operation can impact on the ATC, because in fact we we have been involved in a project on that. Is when, for instance, is in case there is some kind of incapacitation of the pilot or something like that, which are the procedure that from the controller side has to do. But and maybe the other thing that we wanted to analyze in the project that it has not started yet is if there is an overload, the pilot is overloaded because if it's alone or and the pilot has more tasks to do, how these can impact from the instructions. How can this impact on the ground side? Because the controller has to provide instructions to the pilot, and if the pilot is too much overloaded, maybe there could be some incidents or some safety issues. So these are the main aspects that we have identified as important for the ground side. I don't know if I answered to your question.
No, thank you, Patricia. I expected that you would say that, and our experience is very much that the humans are the main form of redundancy in the system when things are likely to go wrong. But I hope that in the coming calls that this is reflected and more money will be directed towards actually researching this, because when you go from taking away the extra body who supports with the communication on the flight deck, the pilots will be looking elsewhere to get that support, and I think that will have quite a big knock-on effect on the ground staff and ATC. So I hope we see that reflected more in the calls coming up. So thanks very much.
You're welcome.
Thank you, Patricia. I think we run out of time, but this was a very interesting presentation for all of us. We're very grateful that you were able to contribute to our session and webinars. There is another, you'll see another question from Lawrence was put on the chat for you, if you can access the chat, Patricia. But let's say, I mean, if they have more questions, can they potentially email you if needed, or?
Okay,
we'll
no problem.
In any case, this was very, very well received by all of us, Patricia, and thanks for sharing your experience in this area, which is.
Okay, it's been a pleasure for me to share all these things with you. Thank you very much.
Thank you, guys, and speak to you soon.
Thank you. Bye-bye.
Bye.
Bye-bye. Bye, Patricia. Bye.